G'day everyone. Today we'll continue our discussion of scattering, talking about partial wave expansion of the wave function. So the idea of what we're going to do today is to expand the wave function, which is both the incoming beam and the scattered wave, in terms of Legendre polynomials. And we can do this because the scattering potential in this course is assumed to be axially symmetric, and so the wave function is axially symmetric. And we can expand any function of theta in terms of Legendre polynomials. The advantage to doing this is that we can then express the elastic scattering in terms of phase shifts for each partial wave. And we only need to use a few of those partial waves for most problems. So we'll find that this expansion gives us a lot of advantages. I've written it here as the Legendre polynomials in terms of the YLM spherical waves that we met when we were doing the Coulomb problem. So let's just remind ourselves of what those Y functions are. So this is the expansion of the Laplacian that we first made when we were looking at the three-dimensional Coulomb problem. And the advantage of doing it in spherical coordinates is that we can separate out the part that depends on the radial direction from the part that depends on the angular directions. And then we can define the spherical harmonics YLM. So the spherical harmonics are the solutions of the angular part of the Laplacian, and the case that we're interested in is the one where we want to have independence of phi, because we want that axial symmetry, that polar symmetry. And so we're going to choose only the m equals 0 YL0 solutions, and they're the ones that we can express in terms of the Legendre polynomials. And so we're a bit familiar by now with these spherical harmonics, and I just wanted to point out that the Legendre polynomials can be expressed in terms of the YL0 spherical harmonics. Additional property of the Legendre polynomials is that they are also eigenfunctions of the angular part of the Laplacian in spherical coordinates, as they must be because they're proportional to YLM. And so I can write that that's true for the Legendre polynomials. And also they have orthogonality relations which are similar to those of the YLM. So like I said, we can write any function with polar symmetry in terms of these Legendre polynomials. And so this is a particular expansion that we're going to use, where we expand the wave function in terms of some coefficient AL, the angular part, which is the Legendre polynomial PL of cos theta, and some function R, which is the radial part. So in particular, we can expand the plane wave. Now, I'm not going to prove that relationship, but we'll do that in the tutorials. The JL functions here are the spherical Bessel functions of the first kind. Nevertheless, we do need to know some properties of the spherical Bessel functions, and in particular, how do they perform at large R? So our plane wave, which is the beam, can then be expressed at very large distances using this formula. So that's expanding out the sign in terms of exponential functions. And this I to the L can also be expressed here. I to the L is, well, I can be expressed as e to the I pi over 2. And so if we take that to the power of L, we get e to the I L pi over 2. So that phase factor I'm going to mix with the exponentials from the sign, and that will give me. And so we see that we have a probability current for the incoming and outgoing waves. Remember, this is just the beam itself. these are equal and opposite for each particular partial wave. So for each L, we have an incoming wave and an outgoing wave, which have exactly the same magnitude. And so there's no net flux towards or away from the origin for each partial wave individually. So there's no net flux towards or away from the origin. So that's the beam. Now let's express the scattered wave in terms of the Legendre polynomials. And remember, the scattered wave here is expressed in terms of this scattering amplitude f, which is a function of theta and k. Last time we didn't worry about the k too much, but now we really want to keep it. And remember that different k's are scattered at different angles. So what have we done here? We've actually replaced this scattering amplitude, which was a function of two variables, with an infinite set from L equals 0 to infinity of functions of one variable, k. And so the question is, why would we do this? It seems like having an infinite set of functions of one variable is worse than having a function of two variables. But remember, I said that at low energies, only the first few ALK are going to be significantly different from zero. And so what we'll be able to do is truncate this sum. Let's see how this will work. So a little diagram here. You've got your scattering center here, and this is the z-axis. You're coming in with some impact parameter b, and you've got some momentum in this direction. And so when you're close to here, you're going to have angular momentum of h bar k, which is the speed at which you're going, dotted with r naught, L equals r cross p, right? And we should put on this also some finite radius here, r naught, which is the range of the potential. So the point is that if you're at b greater than r naught, you will miss the target. So this is a heuristic that kind of enables us to understand why we can truncate this sum. You've got particles which will miss, and then particles which are closer. If this b is large, then the angular momentum is larger, but those are the particles that miss. And so there's some maximum L, which is given by this kb parameter. And if that's of the order of kr naught, then you're at the maximum angular momentum for this problem. Let's do a specific example. So we've got some nucleus with radius of a couple of Fermis, 2 Fermis, let's say, and the incident neutron has an energy of 100 MeV. Remember, the mass of the neutron is of order 940 MeV per c squared, so 100 MeV is still a non-relativistic neutron. So the energy of this, the kinetic energy of this incident neutron is, so that's the momentum of the incoming neutron, and that means that the maximum angular momentum that you're going to have, so this is the maximum angular momentum that you're going to have, because if you're more than 2 Fermi away, then you miss the target and you're not scattered anymore. So in terms of the scattering, all we need to worry about is 430 times 2 Fermi. This 200 MeV Fermi is just a conversion factor which equals 1 in units, h bar equals c equals 1. And so we find that the maximum L that we're going to need to take into account is L max equals 4. In other words, that infinite sum, we're going to be able to truncate at 4. So this is the advantage of the method. Well, so far all that sounds too good to be true, and what we haven't seen yet is how do we then interpret the actual scattering. What we're going to see is that we can interpret all of the scattering in terms of phase shifts. In the previous video, we saw that the wave function must be a solution of this Helmholtz-like equation with a source term on the right-hand side that involves the solution itself. And we've also seen that at large distances, the radial wave functions must reduce to free particle solutions, although they may have a phase shift. Remember, this is just the limit of the spherical Bessel function at large R. So that's the wave function at very large distances, just expanding out that RKL in terms of the exponentials. And what we see is that we've broken this into the incoming part and the outgoing part, as we did before. And the scattering potential U of R only produces outgoing waves. The incoming waves have to be the same as they are for the beam. So we can compare the two at large distances. So if we make a comparison of the incoming wave here and the incoming wave from the beam itself, they must be the same at large distances, and that gives us this formula. And that means that we can write AL equals 2L plus 1 over 2IK e to the I L pi over 2 plus delta L. And that means that we can write the wave function itself at large distances So the wave function has now been written in terms of the beam and the scattered part, and moreover I've been able to take out the factor of e to the IKR on R, which is independent of L, and so this part here is what I wrote previously as the scattering amplitude, F, and we can see that the scattering amplitude F theta, if I compare that one with the one that I obtained earlier in terms of A, then I will get so this is the AL from our previous expansion of the scattered wave, shown here. And because of that, we can then express this part here in terms of the phase shifts, delta L. And that means that the final scattering amplitude can be written as... So what have we learnt here? It means that the outgoing wave has a phase of e to the I times delta L relative to the incoming plane wave. Second thing is that this does not change the total probability current. And lastly, the angular distribution is characterized by the phase shifts. So in fact, the entire scattering problem has been reduced to find these delta L's for each partial wave, and these delta L's will change the angular distribution, f of theta, and this is all that can happen in elastic scattering. Now remember that the total cross-section could be expressed in terms of the scattering amplitudes like so. And now what we can do is we can write that as a sum over the angular momenta of partial total cross sections, so these delta L's are called the partial cross sections. And what we can do is we can actually perform this integral over the thetas. And this part here is just a standard integral for Legendre polynomials. And this factor of 2 pi here is coming from the integral over the phi variable. And so this is an expression for the partial cross sections in terms of the phase shifts delta L. And interestingly, these functions have a maximum because sine squared has a maximum. These have to be smaller than 4 pi over k squared times 2L plus 1. And this is called the unitarity bound. It's the maximum cross section for each partial wave. So we can now write sigma, the total cross section sigma, as a sum of these sine squared delta L's. And we have this property of the Legendre polynomials as well. And that means that we can say that the f of 0, in other words, theta equals 0, the forward direction, and then the imaginary part of this f of 0 can be expressed also in terms of sine squared of delta L. And in fact, we see that we obtain that the total cross section is 4 pi over k times the imaginary part of the forward scattering amplitude. This is known as the optical theorem. And this theorem is really a consequence of the fact that the scattered part, which is this part, is coming from destructive interference in the forward direction where theta equals 0. So you've got the beam, which we assumed went all the way through, and then you've got the scattered part. And we also know from conservation of current that whatever is scattered must be coming out of that forward direction of the beam. And this is expressed through interference, destructive interference in the forward direction at theta equals 0. Last thing before we end today, we'll do an example which will be a callback to the hard sphere that we did 2 lectures ago. And this time we're going to do the quantum hard sphere. So in quantum mechanics language, that means that we have an infinite potential at the boundary and 0 outside of the sphere itself. The boundary condition in that case is easily stated. Now outside, we have to have the most general form ever for an outgoing plane wave, outgoing spherical wave. We'll write as the sum of an outgoing Bessel function of the first kind and a Bessel function of the second kind, which is YL of KR. And the Bessel function of the second kind is not well behaved at r equals 0, but that's not a problem for us because we are going to have the boundary condition at the surface of the sphere A instead. So we need to include that spherical Bessel function of the second kind as well. And so AL and BL are set at the boundary condition r equals A by this formula. This is the asymptotic form of the spherical Bessel function of the first kind and the spherical Bessel function of the second kind. And so in the limit we can write this gives us a expression for the phase shifts here in terms of these BL and AL, which are set at the boundary conditions. And so, for example, the L equals 0 term is given by tan to the minus 1 of In this case, the L equals 0 phase shift has a particularly simple form. So what's happened here is that the hard sphere has pushed out the wave function so that the oscillations are starting at r is equal to a instead of starting at r equals 0. And for low energy scattering, this Ka is going to be much, much less than 1. In the limit of small ka, we're going to have, and these are just standard expressions that come from like fancy mathematics, which we don't need to worry about. We just take it as given. So for small values of Ka, we're going to get that this ratio of JL over JL over YL is going to be approximately equal to something like Ka to the power of 2L plus 1. And Ka is small, so tan delta is approximately equal to delta. And so we see that higher angular momentum here are suppressed as we expect. So in other words, if we have a very small Ka, then the higher angular momentum, L equals 1, 2, 3, and so on, are very suppressed compared to L equals 0. So in the limit that we have Ka tends towards 0, so very, very small scattering, only L equals 0 contributes. Remember, we've already worked out that delta naught is equal to minus Ka. And if we go back up to our expression for the total scattering amplitude here, given by this formula, and sigma being a sum over those, so then delta L naught is going to be 4 pi over K squared times 2L plus 1 sine squared delta L. And we can write that as sine squared delta naught is going to be Ka squared, because for small angles, sine delta naught is equal to delta naught. And so this is going to be nothing but 4 pi A squared. Interestingly, this is 4 times the size of the classical cross-section, the classical scattering cross-section that we worked out a couple of lectures ago. So we see that in the quantum case, it kind of fills out this whole 4 pi, which is the surface area of the hard sphere, rather than the cross-sectional area of the hard sphere. And so you get a slightly different answer to the classical case. Well, I think that's enough for today. Thanks for listening, and I'll see you next time.